So welcome everyone. I'll just give a bit of a preamble before we get started. I know, use the right window. So I'm going to give you a sort of overview of parallel I/O. There are two separate talks here. The first one is a general overview of parallel I/O because it's not. I find it quite confusing. So I'm trying to give you the basic concepts of how it works. And definitely this first lecture, which is actually drawn from the Advanced Message Passing Programming course, is a very general overview and will be relevant to any parallel machine you're using. The second lecture is shorter and it has recent preliminary results from ARCHER2. But again, a lot of what I say there is generic to almost all parallel systems. That's partly because actually Lustre, which is the parallel file system which is used on ARCHER2, is pretty ubiquitous now. So I'll start off, I said, with a general overview. Now, just in general, please ask questions. As I said, you can use chat at any time. I'm monitoring the chat, or you can use audio if you want to follow up later on. Maybe during, there'll be chance at the end for a Q&A. But if you have any, please ask any questions you want during the talk. And probably best to use the chat. So this lecture is being recorded, and the recording will appear on the ARCHER2 website quite shortly. So first of all, I don't sort of very general idea of why is I/O hard. I mean, when you write a program, you have this nice view that you have a process running or multiple processes for a parallel program, and they have their memory and all kinds of things, and that's all, you know, virtualized and handled for you by the operating system. You know, when you write a file, the data from the memory has to physically appear on an external device, in a physical spinning disk. Files are very restrictive. I mean, of course, you can put metadata in them, but access is kind of, you know, they're not, although you can access all different parts of a file, there's a big cost. And when you write a file, you really want to write it linearly from the start to the end, and that might involve remapping your program data. Your program data might not be in a format which lends itself to that. Fundamentally, just a string of bytes with no memory of their meaning, although modern I/O systems will have metadata attached, of course. There's lots of system-specific I/O options to I/O. You know, you have text, binary, big little endian, the bane of my life, fortran unformatted, HDFI, NetCDF. You know, there's all these different options. So disk systems themselves are very complicated. When I say a disk, it's probably not a single disk. It's a RAID, a redundant array of independent disks for bandwidth and for parity checking and resilience. There's lots of layers of caching. You know, when you write to disk, it may not write to disk at all. It may write to memory. It's all very complicated. I think I/O is the HPC equivalent of printing. You know, you buy your nice new fancy computer, it all works, and then you try and print something, which is get some data onto a physical external device, and it's a nightmare. So why is parallel I/O harder? Well, now I should say before I go forward, all this is very much my view as an applications programmer. Some of the things I'm saying, and please speak up if I'm saying it's not true, may not be strictly true in the absolute detail, but they're a general overview of how things seem to work from the application programmer's side and the things you need to worry about. But please chime in if I'm saying things which are actually not strictly true, if you have more knowledge than I do about the implementation. The main problem is why is parallel I/O harder is you cannot have multiple processes write into a single file easily. Unix generally can't cope with this. Unix I/O assumes that any file is only being at least written to definitely by one process at once. I don't know if you've ever used a shared file system and had two people editing the same file at the same time. It's a complete disaster. Because it turns out that, you know, the data, the main reason for this is you know, Unix, and it's what we all say Linux now, wasn't designed for parallelism, not in its early days. But it's not even sufficient to have processes writing to distinct parts of a file. And I'll just illustrate that in the next slide. A lot of people think, well, okay, why can't I've got a file and I want 4 processes to write to it. These might be your MPI processes. Why do I just have one process write the first quarter? The next process will seek to a quarter of the way in, write the next quarter. We'll just seek to the correct place and write the data. Well, that doesn't work. Even reading can be difficult. File systems weren't designed to have thousands of processes reading a file at the same time. So that's the prime point. But another point is your data is distributed across different processes, and the processes in general own contiguous chunks of the file. You will see in a very simple example, the data from your multiple processes are going to have to be remapped in quite a complicated fashion to produce the file that you want on disk. And other things in a parallel program, you may have halos on your local. So there's a whole bunch of complications. But I just thought I'd show this diagram to show you what the problem is. Why can't you just have all the MPI processes, your parallel processes, open the file and seek to the correct place? The problem is that there's a lot of caching going on. The caching is there to make I/O fast. I mean, the modern memory is cripplingly slow, so we have memory caches. So when you write, the way to make writing to memory fast is not to write to memory at all. Write to a cache, which is much faster. The same is true of disks. To write a file quickly, don't write to file. Write to some cache, which might be in memory. So what we have is we have a single file. We're going to imagine two processes, process 0 and process 1 are going to be opening that file. Now, it turns out that that file happens to sit across 3 disk blocks. Disk blocks are typically maybe 4K, or in an HPC system, they might be bigger. But what happens is the I/O system doesn't understand there's multiple processes. So process 0 says, I want to read the data. I actually only want to read this first half of the data up to here. But actually, you can only do transactions in terms of a complete disk block. So what actually happens when you try and read this data is that the disk cache, the operating system gives you 2 disk blocks in your disk cache, and then you read some of that into your process, and that happens on both so both processes get what they want. Process 0 has read the first half of the file, process 1 has read the second half of the file, but they've actually cached more than they needed because everything happens in transactions to hold an entire disk block. That all seems fine. Then process 0 updates its data, process updates its data, and then you write. Okay, so you form a write. Now, when you do a write, it probably doesn't go to disk. It probably goes to a disk cache. So you alter the first 3/4 of your disk cache. So that all looks fine. Okay, you've got a local cache copy of your I/O. That's fine. Sometime later on, probably when your processes end, when your program ends, the operating system is going to say, well, I better flush this data actually to disk, because you can't leave it in the cache all the time. It needs to appear on disk at some point. And the problem here is that each process thinks it's the only process that's altered the file. And so process 0 flushes its disk cache there, but process 1 flushes its disk cache, and you get corrupt data. You can only have multiple processes accessing the same file if you align the access on one of these disk blocks, and that's way too complicated to worry about. To really give you a feeling for why, I/O is quite complicated. There's lots of caching going on. And fundamentally, Unix wasn't designed with parallel programming in mind, and so the I/O systems all assume that they're the only process doing the I/O. But that's something of an aside, but I think it's interesting to get your head around that. So what is a parallel file system? I remember when I first used a parallel file system, I was using one. I thought, I don't really know what is a parallel file system. Well, what's a parallel computer? A modern parallel computer is constructed of many standard processors, each not particularly fast, and the performance comes from having lots of them at once. Okay, so that's what we do. The new ARCHER2 system will have 750,000 CPU cores, whereas your laptop probably has 2 or 4. But to do that, so each processor isn't particularly fast, but you have potentially hundreds of thousands of them. But to make use of that requires you, the user, to manually distribute the data and the calculation across processors, and that's the act of parallel programming, almost universally now using MPI. You have to decide when you write your program, how is the data and the calculation going to be distributed across processors? And that's building a parallel computer is quite difficult, but then a lot of the issues then passed on to the programmer. Parallel file systems take the same approach. They're constructed from standard disks, many standard disks. What I'm saying is, in the early days of parallel computing, a lot of people thought they could run their serial program on this magic supercomputer and it would go faster. Well, often it would go slower because the processors might actually be a bit slower than in your laptop. And so, I mean, everyone much more aware of what parallel programming is now, but in the very early days of parallel computing, people were often surprised that their programs ran slower on the supercomputer than they did on their desktop machine. And the same is true of parallel file systems. They're constructed from many disks, each not particularly fast, and the performance comes from reading and writing to many disks at once. And that requires the way the parallel file system sees lots of clients. Okay? A parallel file system is really a distributed file system. It sees lots of clients, and for a parallel computer, each client is a separate node. So each node of your computer, a node is running its own operating system, appears as a separate I/O client. So on ARCHER2, we will have aboard of 5,000 or 6,000 nodes, each with 128 CPU cores. So the parallel file system will see about 6,000 clients, all wanting to read and write to its many disks at the same time. But the performance comes from reading and writing to many disks at once. And there's two ways you can do that. One is you can have lots of files stored on different disks. That's not particularly elegant, as we'll see later on, but what a parallel file system can do is data from a single file can be striped across many disks. And that's how we're going to get into our aggregate I/O performance for big parallel programs. We're going to have a large file that we're reading and writing to, but we're going to ensure that that file is stored on many disks, and so that we can get parallelism with the access to the disks. But that does require some manual intervention from you, the user, in the same way that, not as much as with the parallel programming, but it's not for free. Luckily though, although the data from a single file is striped across many disks, when you do an LS, you don't see 12 or 20 different files, you see one logical file. The fact it's striped is slightly hidden from you, and that's because there's a single database which has overall control of the file system. This is called the metadata server. This is Lustre speak, actually, but Lustre is the parallel file system we use on Archer and ARCHER2, and it's pretty universal now across parallel computers. So we have many disks. I'm being slightly naive here, calling them disks. They're not quite disks, but that's what I think of them as. And we have one database, the metadata server. So this gives you what a parallel file system looks like. Your application has many processes running on many compute nodes. Each one of these is actually, you should think of each process has its own memory in a distributed computer. But really, I really should have labeled these as nodes. Each node appears as a separate client to the file system. Our file system is under the control of one metadata server, and there's some high-speed network that allows all these processes to talk to all these disks. Now, at the lowest level, we have lots of RAID devices, which I call disks. Technically, they're called object storage targets in Lustre speak, but I will synonymously call them as disks because they're the sort of the lowest level entity. And so the terminology now these are actually aggregated together in object storage servers, but that's not particularly meaningful. My basic understanding of the way a parallel file system works is you have lots of nodes, each of which appears as a separate I/O client, a network to allow them all to speak to all these disks down here. So we will talk about nodes, and we'll talk about OSTs or disks, each of which is like a separate disk. And there's one metadata server that controls all of this. So whenever you talk to these disks, you have to first of all talk to the metadata server. For example, to ask, well, where is my file stored? It might be stored on which disk, which OST is it stored on? Is it stored on multiple OSTs, for example? So we'll come back to that diagram later on. This is just a picture, actually. I only have a picture of Archer's storage system, but they look very nice. They look very high tech. And there's a metadata server, and you have lots of racks stuck together into big. So you have these massive disk units. So basically, this disk unit, this has hundreds and hundreds and hundreds of spinning disks, but they're arranged in this hierarchy of. So I naively called this thing down here at the bottom, an object storage target, a disk. It's not really a disk. On Archer, it was actually each object storage target actually had 10 disks. That's 8 for your data plus 2 for parity checking and redundancy. But I think that's below the level you could address it at. So I will synonymously say disk and object storage target, being a bit loose there. But it's just quite a nice picture to see these things. So how can you actually benefit from the metadata server? Well, you can do independent I/O, and this is often people's first stop shop. They're running 1,000 MPI processes and they want to write their data, so they just get each process to write its own data file. And by default, each file will be stored in a single OST. but the metadata server will assign different files to different disks. So in principle, this achieves really good bandwidth, because you're writing from your program here, you're writing thousands of files, and they're stored in some distributed way across these OSTs. So you're using all the disks at once. That sounds like a really good thing to do. And so in principle, this achieves maximum bandwidth. But there's two problems with this. It's a nightmare to cope with in practice. You run a parallel program, you end up with 1,000 files. That's just a nightmare. So you really want, like your serial program does, to produce one output file. Also, opening and closing files is serialized via single MDS. Every time you open or close a file, you have to speak to the metadata server. And this can actually be a performance bottleneck. The metadata server, and on ARCHER2, it may not be true, but on ARCHER, the metadata server got quite easily overloaded. And you might say, well, you know, I'm only writing 1,000 files, but yes, every other user on the system might be writing 1,000 files as well, and the I/O system is of course shared between all of you. What are the mitigations? Well, one mitigation you can do when you set up the computer is not to have a single file system with lots of OSTs and one metadata server. You have, and we'll see this is what's done on ARCHER2 and was done on ARCHER. We have three file systems, each with a fewer number of disks, fewer OSTs, but each has their own metadata server, and that gives you some balance between the latency and bandwidth. Or you can write a file per node rather than a file per process. Remember, each node of your parallel computer is one client. There's not really any performance advantages, particularly of writing a file per process. So if you do a file per node, you'll do more than 100 times fewer files on ARCHER2, because it's 128 CPU cores per node. So that can be, there's a mitigation. There are solutions, but they're mitigations. One is a hardware setup, and the other is what you and a user can do, file per node. But the really interesting thing is, you want to write a single file. You want your program to produce a single output file, and Lustre allows you to get improved bandwidth to a single file. You have a single logical user file, but the operating system, the file system, divides the file into stripes, but you have to request that. We'll see the default on ARCHER2 is to store a file on a single OST, not to stripe, but it's very easy to ask for striping. And once a file is striped, the stripes are all stored on different OSTs, different physical disks, and you can be read, written to from their assigned OST in parallel. So this allows you to do genuine parallel I/O, using multiple disks, but getting increased bandwidth because it's a single logical file which the operating system or the parallel file system has arranged to be stored across multiple disks, multiple OSTs. So data striping is the key concept of allowing you to get increased bandwidth to benefit from parallelism of a parallel file system, but from still only having a single file, which is really what you want just for usability. So a parallel file system allows multiple I/O processes to access the same file through this data striping. It's typically optimized for bandwidth, not for latency. Parallel file systems are optimized for saying, could you please write 100 gigabytes of data? Reading and writing small amounts of data, jumping around in the file is very inefficient. Okay? So that's something to watch out about. However, all this parallelism is very difficult for a general user to configure and use. So we need some kind of higher level abstraction which allow you, the user, to focus on what you're interested in, the data layout across user processes, and for the parallel file system to cope with all the other stuff. And there are a number of libraries you can do with this, but I'm going to talk about a few here. This talk was originally from an advanced MPI course, so I mentioned a bit about how MPI-IO does this, but the concepts are the same for all the other libraries you might use. Now, just to illustrate why this can get complicated, I'll come back to this diagram. Imagine I'm doing a very, very simple, tiny calculation. Okay, I've got a 4x4 array on 4 processes distributed in a 2x2 grid. This is so each process has a 2D array which has 4 elements, 1, 2, 3, and 4. But we're thinking of them in our MPI program as actually being small subsets of a larger 4x4 array. Okay. If I then want to write this data out in the same order as if I was writing it from a serial program, on the way I've written it, I'm assuming the data is contiguous in this direction just for the sake of argument. Okay. But no matter which way you assume the data, if you want to write this data out, which is distributed across multiple processes, in the same way as if you wrote it from a single controller process, you can see that you've got the data from the yellow process, the blue process, the yellow process, the blue process, then the green process, the red, the green, red. And the problem here is twofold. The mapping from your program data to the file is quite complicated. And this is an almost trivial example, a 4x4 array on 4 processes. Imagine a real example. It's very, and also no process owns a big contiguous chunk of the file. So if you want to write your data, you're gonna have to write the data, and then skip, and then write, and then lots of skipping, which is slow. And also somebody else might be writing at the same time. And we saw that's a problem. So you have to understand that the mapping from your program data, which is distributed in an MPI program, to the file can be very complicated at the lowest level. So what are the naive solutions in message passing? Well, we can use controller I/O, send all the data to and from a single controller process, and read and write a single file. Now, we can quickly run out of memory on the controller, but that's not so much of a problem. But the main point is this does not benefit from a parallel file system. If we go back, we're going to talk what's going to happen later on. If we nominate this process as the controller, okay, probably this link here from the process to the network is going to be the bottleneck. It's very hard. We're not going to benefit much from the parallel file system because we're going to be throttled by how quickly a single node, a single process can write to disk. So what we do in this naive approach is we gather all the data from all the processes onto one controller process, typically MPI rank 0, and then we just write using our normal Fortran or C read and write routines. That's not going to give us any good performance. We can write separate files. On a normal cluster system, you may actually have local disks, and each process is write to a local file system. We don't have local disk on ARCHER2, but each process opens a unique file, data xxx.dat, and writes to it. As we've seen, that can overload the file system, and it's a nightmare at the end. So this is slow, but at least produces what you want, a single file. This is fast, but a bit of a nightmare. Because the major problem is with separate files of reassembling the data at the end. You end up with lots of pre and post-processing steps. At least reads and writes are in parallel, but it really isn't very elegant. And it may overload the file system for many processes. The metadata server may not be able to keep up with all these thousands of separate requests, and that becomes the bottleneck. And just a little, you may, although you think that your data is distributed across a 2D array, the computer, this is actually a picture of Hector, an ancient computer, all it sees is 4 processes, each with arrays of length 4. By default, the computer, the file system doesn't, your view of your data is very different so you're going to have to tell the parallel file system, your I/O library, that actually the data is arranged in a particular pattern. By default, it doesn't know that, because that's a decision you, the programmer, has made deep inside the bowels of your MPI program. So the MPIO approach, I'm not going to try and tell, but it's the same approach that all these libraries take, is that each process needs to describe what subset of the global data it holds. It needs to say, look, there's this global data, which is the file, and I own this subsection of it. And it's entirely up to you to get that right. But MPI-IO is probably quite low level now, but it does it in quite an elegant way. What you do is each process says, okay, to the I/O library, which here is MPI-IO. Okay, I'm thinking of the data, excuse me, I'm thinking of data of being a large 4x4 array. Of course, the dimensions would be huge, much bigger. I'm the green process. I own the bottom right-hand corner. So each of these processes individually tells the I/O library which bits of the file, the mythical global array, it owns. And actually, MPI uses derived data types to do this. But that's what you do, and all these I/O libraries will have the same approach. There'll be some setup phase where you say, okay, we're all going to write the same file, but this is the part I own. I own this 3D subsection of this big 3D array. There may be ways of describing more general unstructured patterns as well, but there will be some phase which MPI calls setting the file view, but other libraries have their own phase where you say to the I/O library, this is the data in the file that I'm in charge of, that I want to read or want to write. So there are other parallel I/O libraries. MPI-IO is probably the lowest level one. You might not call it directly now. Higher level libraries exist. A lot of people use HDF5. NetCDF is one the climate people use, climate and weather researchers. ADIOS is a library which actually allows you to interface to all these. But the approach is the same in them all. There'll be some way of describing what portions of the file each process owns. And why MPI-IO is still important is that these libraries will all use MPI-IO, usually use MPI-IO at the lowest level to do their reads and writes. So actually, if you understand the performance of MPI-IO, which is what I tended to look at, you typically understand the performance of these higher level libraries because they actually funnel through MPI-IO. I mean, if you're going to write a parallel HDF5 library, you're not going to reinvent the wheel. You're going to say, well, the MPI-IO standard does that all for me. I'll just call MPI-IO and rely on HPE or whoever writes your IO libraries has done a good job. So that's really a very high level sort of general view of IO. Parallel IO is difficult in theory and practice. MPI-IO provides this high level abstraction. I'm not going into the syntax details. I said it hides all the system-specific file system details from you. And more flexible modern formats like NetCDF and HDF5, and I also mentioned ADIOS, gain performance by layering on top of MPI-IO. If I were doing the advanced message passing course, I would now go on and go through how MPI-derived data types work. But we're not going to do that. We're going to now go into a lecture which focuses a bit more on the specifics of ARCHER2. So I'm just get that next lecture lined up because it is in a different slide deck. It was a talk I originally designed for the Asimov project, but I've extended it somewhat here. Are there any questions about that? As I said, that's very much my sort of naive application programmer view of the way things work. I think it's generally conceptually correct, but it may be not absolutely correct in every detail, but it gives the right flavor of the feeling for how parallel IO works. Okay, so for setting a file view. Okay, that's a very good question. So I'm going to talk about the bottlenecks later on, but typically there's very little. It's really a very, very little overhead. It will be a very quick call. Well, it's collective, so all the processes have to get together. But there will be some overhead, but not a lot. But I should have said this actually. The kind of bandwidth you get on the interconnect internal to your parallel program will typically be much faster than your bandwidth to disk. And so actually we'll see that the way that IO libraries work to get efficient IO is they do a lot of rearrangement before they write to disk. So writing to disk is really probably the slowest thing you can do. The software and the communications overheads from within your parallel program are typically, in my experience, much smaller than the overhead of actually writing to disk. So for that particular question, I would say it would be very small. But because the general reason is, I'm not saying it's but your first approximation, stuff you do within your parallel computes with its very, very high speed network, on a very high-end system like ARCHER2, will be much quicker than disks are very slow, comparatively slow. That's a good question though. I'll give some ballpark figures later on. So I'm going to ask you, what are the bottlenecks? Okay, so we have this system where we have lots of disks. These are object storage targets. We have this metadata server. We have there's a high-speed network, but each of these nodes has to get pump data out into that. What are the bottlenecks? You know, what limits the performance? And my sort of experiments, and we're only finding out ARCHER2 finding out about ARCHER2, it's still quite new to us, is that the overheads are down here, not up here. But I'll show you some performance numbers which hopefully will illustrate what you should be getting. So the ARCHER2 hardware, there will be 3 separate /work file systems. So this is, where we've taken this decision. We have 36 of these object storage targets, these disk units, but we're not putting them into a single, and this was exactly the same as was done on ARCHER as well. If you're an ARCHER user, we don't put them into a single large file system because that means that there'll be could be too much load on the metadata server. So we have 3 separate file systems, and you'll be assigned. You won't see this, but you're each on a consortium, on a project basis, you're assigned to a different one of these file systems, we have 3 of them. So each of these has 12 OSTs. So that immediately says that the maximum striping you can get on a file on ARCHER2 is 12. It was much higher on ARCHER. ARCHER had a larger number of not so fast disks. The striping on ARCHER went up to about 50, I think. So, but the ARCHER2 disks seem to be much faster, and so that we need fewer of them. There is actually an additional file system with solid-state disks, not spinning disks. This is yet to be configured, and probably I think it might be used for sort of scratch space. But we'll expect better performance for small I/O transactions because, you know, if you have a solid-state disk, it's more like memory. You can do random access much quicker than a spinning disk where you have to physically move ahead. Better latency, but not necessarily better bandwidth. We're still investigating that. But each of these 4 file systems has around 3.3 petabytes of storage, which gives you 13.2 petabytes. Then I looked up the documentation and it said there was 14.5, but that's because at these levels, 2 to the power of 40 is quite a bit bigger than one. I can't get the right number of zeros here. A kilobyte is 1024 bytes. It's a bit bigger than 1000. That's only a few percent. But I can't know what a petabyte is. It should be actually, is that 10 to the power of, oh, 2 to the power, this is embarrassing. 2 to the power of 40. Is that 10 to the power of 30? I'm not sure that's right. Whatever it is. It matters that it's power of 2. So it's actually 10% more. A petabyte, the binary one, is about 10% bigger than a petabyte. That's right. Got that figure from. But you know, you've got 3 or 4 petabytes in each of 4 file systems, 3 of which are going to be standard spinning disks, 1 of which is a solid state array, which is yet to be fully configured. So if you're using serial I/O, you're not using any parallel libraries. What you're doing is you're doing a single file with controller I/O, a single writer, or you might file per processor, file per node. But in each case, you're just opening a single. In the first case, you're opening file.dat, gathering the data using MPI and writing a single array, a single file. In the second one, you're opening lots of files, but each process is, or each node is only doing serial I/O. In that case, there's little point. Oh, thanks, Juan. 2 to the 50. That's thanks. So, there's little point in striping the file because a single file, there's no point. We're already writing multiple. Sorry, if you're writing a single file, the performance bottlenecks appear to be elsewhere. Multiple files is already parallel as we're using many disks. So actually, the default on ARCHER2, and it was on ARCHER, at least in the latter stages of ARCHER, is a single stripe is the default. And this sometimes surprises people, but it's because for a lot of cases, that's what you want. Now, my ballpark figure is that each OST maxes out at just over 1 gig. Now, that actually, this might be slightly wrong. The bottlenecks may be elsewhere. But if you're going to be doing serial I/O, either from a single controller process or from multiple processes, you're looking at being able to get about 1 gigabyte for each of them. 1 gigabyte per node, or 1 gigabyte from your controller process. So my ballpark figure is that each of these OSTs is going to give you about 1 gigabyte a second. Now it might be a bit more complicated than that, but that's the sort of a ballpark. You're going to want gigabytes per second for serial I/O, which isn't very fast, given that you've got petabytes of huge amounts of memory. I mean, each node on ARCHER2 will have 256 gigabytes of data of memory. So disks are quite slow, relatively slow. So I have a very simple benchmark, which was development of some work which some colleagues of mine, Adrian and Fiona, did back a long time ago, which takes a large distributed, it's still very simple, it takes a large distributed 3D array. I did 256 gigabytes on 2048 processes, and I write to a single. I write this out in lots of different ways. This was tested during initial access period to the production system, and on an otherwise empty machine. So these are not to be exceeded figures. But I got that about, if I wrote to an unstriped file, I get about 1.2 gigabytes per second. You get I've reached this time my terminology. Apologies for this mistake. I've not completely updated on my slides. If you stripe that file, you actually get reduced bandwidth, because it looks like each node can only write about a gigabyte a second. And if you stripe the file, then the file system has to remember where each, or does that go on this disk or that? So for control writing serial, it looks like you don't want to stripe the file. When you file per process, I get 80 gigabytes per second. That I think is not a genuine result. I think it's being highly cached, because this file system was completely empty. I was about the only user on it, and so these high rates are not seen on the 4-cabinet system in production. So I think that massive rate was getting, I believe, was due to file caching. So I would expect that you wouldn't get about much more than a few tens of gigabytes per second for file per process, because you have 12 OSTs in each file system, each of which can support a gigabyte or so a second. So I think that my file per process results were anomalously high. If I do file per node on 16 nodes, I got about around 18 gigabytes per second. So actually, it implies limiting factors the I/O speed from each node and not the speed of the disk. So that's saying that actually each of these disks is faster than the rate at which a single node can pump out data. So actually, the I/O speed scales for the number of nodes you have writing, not the number of disks. So you can get more than, I said that you've got 12 disks here, each of which can do about a gigabyte a second. It actually might be that it's slightly more complicated than that. But I would expect that the maximum I/O bandwidth you're going to get is going to be a few in the tens of gigabytes per second. That's my ballpark figure. Okay. I think all these results to many files are useful to understand the bottlenecks, but I think we really care about parallel I/O to a single file, and so we need to stripe a single file to get any parallelism. But we saw that by default, files weren't striped. Files were stored on a single OST, single disk. How do we stripe? Well, the easiest thing to do is a very simple command, and I find it much easier to set the striping on a directory. You can do it on a directory or a file, but it's much easier to do it on a directory. It's LFS set stripe, and then you see how many stripes minus the stripe count, and then you do it on a directory or a file. And if you say n stripe equals 1, it gets full striping. So what I do if I want to do parallel I/O is I create an output file called results, and I do LFS set stripe minus C minus 1 results. And that will then mean that files which are subsequently created in that directory will be striped across multiple disks. It doesn't alter the striping for existing files. You have to require that requires a copy. If you want to get the number of stripes, use getStripe. I say here the getStripe output is much more readable for files and directories. That doesn't seem to be true on ARCHER2. That's actually a comment on that for ARCHER, possibly. But definitely, the way to control your I/O is to have separate directories for your output files and change the striping on those output directory or directories. And that will then be inherited by all the files which you created in that directory. So for parallel I/O, you should set maximal striping. So I take a step back. So how do you do good parallel I/O on ARCHER2? Well, if you're doing parallel I/O, you are using a parallel I/O library like MPI-IO, HDF5, and many modern applications already have this implemented in them. You should set the maximal striping, because by default, you will not gain from this because your file will be stored on a single disk. The other thing I would say, though, is if you are developing your own code, use collective I/O. So what I know for what MPIO does is if you do, there will be 2 formats of all the output routines. There'll be one which is collective and one is individual. If your I/O is individual, what you're saying is this process is doing I/O, but it might be the only process. The other processes might not be doing it. That means the parallel file system has to process each individual transaction independently. You get a large number of small I/O transactions. That is very bad. What you want to do is you want to tell the I/O system, look, we're all writing at the same time. And what MPI-IO does there, okay, that's fine. All the 10,000 processes are writing, but what I'll do is I'll pick a dozen aggregator nodes, one for each OST. I'll reshuffle the data using MPI so that each of these aggregator nodes has the data it needs, and then they'll write in parallel. And so instead of having a large number of small I/O transactions, you will get a small number of large I/O transactions. So almost all these libraries will have collective and non-collective I/O, and you really have to do collective I/O, otherwise your bandwidths are terrible. Finally, I would say if you ever have a query, please quantify your I/O speeds in gigabytes per second. You know, I mean, I appreciate you want to contact us about I/O, but I mean, my I/O is slow. It's not particularly useful because your I/O might take a long time because you have a large data set. But if you're getting 20 gigabytes per second, for example, then that's probably quite good. I would not expect you to achieve more than 12 gigabytes per second for the default parallel I/O settings. We may be able to improve that by tuning MPI-IO slightly. I want to investigate that. But you're talking about a few tens of gigabytes per second. It will be doing well. So just to say why collective I/O is so important, here's my classic diagram of the 4x4 array on a 2x2 grid. And imagine that I've striped this file across 4 disks. Okay, if I do independent I/O, okay, this yellow process has to write data to disk 1 and disk 2. So first of all, it's doing a couple of small transactions. But more than that, when it's writing to disk 1, it probably has to lock the file on disk 1 because it says, well, I'm writing to this, but other people might want to write to it as well. I need to lock them out, okay? So not only does independent I/O lead to a large number of small I/O transactions, it leads to an enormous amount of file locking because every time a process accesses a file on a disk, it has to lock that file. So what will happen is the yellow process will lock disk 1, the blue process won't be able to get in, it will do its small write, unlock it, then the blue process, everything's serialized and incredibly slow. If you do collective I/O, the file system, your library, your parallel I/O library, say, okay, right, okay. If I collect the data from the yellow process and the blue process together, I can then write it in a single big chunk. They're the only people writing to the disk. I don't need to lock the file. So you get a small number of large I/O transactions and you get almost no file locking. So collective I/O is absolutely crucial. So the two things to getting good parallel I/O performance are use collective I/O and strike the output file across multiple disks. And so non-collective I/O is actually too slow to measure. I was getting a few megabytes a second, not gigabytes. So it's for real complicated I/O patterns, it's cripplingly slow. This is where it gets slightly complicated. Collective I/O uses MPI collectives. What it will do, the approach the I/O library will take, is to redistribute the data within your parallel. This is all done under the hood. Redistribute the data within your parallel computer using MPI collectives, and then do writes. The default performance of the MPI collectives is poor with the default settings. And so we need to set a magic variable. This is documented, FI, OFI, RXMX, SAR limit equals 64K. I don't know what it does, but it improves the collective performance. Oh, if we do that, then collective I/O, so I'm writing this, how big was it, this file? Can't remember how big my file was. 256 gigabyte file on 2K processes. We're going to write that all to a single file using a single MPI write call. We get about 11 gigabytes per second for the HDF5 and the NetCDF libraries. For an unstriped file, we still get 1 gigabyte per second. So again, this is saying you go to all this effort of using collective I/O and a parallel I/O library, you get no faster than just writing from a single controller process. That's because you have to stripe the file. So you actually get almost linear speed up, just under a gigabyte per second for the unstriped, about 11 gigabytes per second for 12 stripes. For MPI-IO, we get less than that, which is weird because HDF5 calls MPI-IO. So there's something slightly strange going on here, which it's an unfortunate issue with at the moment. That so if using HDF5, what's the optimal number of stripes? I believe if you're using parallel HDF5 and it's well written, it will be 12. But you should specify -1. You should do LFS set stripe -C -1, which tells the Lustre system to use the maximum number of stripes, which happens to be 12. But you should, I would not normally say 12, I would say -1, because on another system, there might be more than 12 OSTs. There might be 20 or 30 or 40 or something. Is that okay? So yes, on ARCHER2, it's 12, but use -C -1. So this is a slight unfortunate thing, which we'll hopefully get ironed out later on. But on ARCHER2, there are two very low-level network protocols. OFI, the default, the Open Fabrics interface, also something called UCX, which is developed by Mellanox. And UCX seems to be better for collectives with heavy comms loads. It also seems to improve parallel I/O. So it's rather complicated on the current system to do this. On the production system, it will be much simpler. But what you fundamentally have to do is you have to swap. You have to say, sorry, apologies. You have to say, instead of using the Cray network OFI interface, use the Cray network UCX interface. And instead of using the standard Cray MPEG, you use Cray MPEG UCX. There's a bit of jiggery-pokery here due to the way modules work on the current system, which is a bit annoying, but it's much simpler on the production system. Will be much simpler on the production system. And this helps parallel I/O, and this restores our performance hierarchy. MPI-IO is a bit later. They all get about 11 gigabytes per second. Now, my previous assumption had been that we got 11 gigabytes per second because we're saturating each of the 11 OSTs. That might not be true. It might be that that we need more aggregator nodes. We actually might be better to have more than one node writing to each disk. So my next thing to investigate is you can configure. By default, the MPI library picks one writer, one aggregator, one I/O node for each OST, but it might be better to pick more than one, simply because the disks are much faster than they used to be. So I need to check that. The conclusions for parallel I/O to a single shared file: use a high-level parallel I/O library, MPI-IO, HDF5, or one of these other ones. Use collective calls and strike the file across all OSTs. For serial I/O, which could be the controller I/O, which is single or multiple files, don't strike the files, except the defaults on ARCHER2, but consider possibly writing a file per node. It will reduce your number of output files from file per process to by over 100. If you use controller I/O, it only uses a single disk. So the two extremes are controller I/O only uses a single disk, file per process may overload the metadata server. So a file per node is often a medium thing. The problem with file per node is you still end up with multiple files. But for serial I/O, if you're using just basic C or Fortran read-write routines, but relying on there being multiple writers with multiple MPI processes, don't strike the files. But if you're using a high-level parallel I/O library, you should make sure you're using collective calls and that you strike the file across all the OSTs with -C -1. So that was a bit of a. I hope that made some sense. It was a bit of a high-level overview and then some numbers. But if you're using a high-level I/O library and you strike the disk, you strike the file, and you've got big files, I would expect your I/O rate should be in the tens of gigabytes per second. Maybe 10, you might be able to get more, but that's the kind of numbers you should be getting. If you're seeing 1 gigabyte per second, you're probably doing serial I/O somewhere along the line. Either you're not using a parallel I/O library, or you've not striped your file, or you're only writing one file at one time. The one thing I haven't said. So I don't know. So my assumption had been that the I/O was limited by the OS. My assumption had been, and I believe this was true on Archer, where the disks weren't nearly as fast. You were limited by the performance of each OST. Therefore, the right thing to do is to have the same number of aggregator nodes as OSTs, which is the default performance, and that would say you'll never get more than 12 gigabytes per second for collective parallel I/O. However, it might be that each OST can do more than 1 per second, so we might want to raise that, and there is a way of independently changing the number of aggregators. It's a non-default setting, but you can change an environment variable. So I don't know, but I'm guessing maybe 20, but I don't know. Also, in production, you're always sharing the whole file system with all other users. So, you know, you might just be on a bad day where someone else is doing parallel I/O to your work system as well. So, but that's what I want to. Yeah, I think it is limited by the aggregation nodes, and I think it might be worth increasing that default limit, but I haven't had a chance to play around with that yet. But I think, you know, I would be surprised if you can get more than a few tens of gigabytes per second. I mean, that's pretty good, but I'm thinking that's going to be your limit. That's my guess. So actually, that doesn't. So that's a bit. The question says, a common use of using one MPI processor per node with many OpenMP threads. This approach prevents one from making maximal use of MPI-IO. What do you think of this? So I don't think it does actually, because again, these are my observations. The file system doesn't see many processes; it sees many nodes. Fundamentally, the file system thinks that there's one. That the writing is coming from one node. So I would have said by naively that actually having one MPI processors writing per node will get you the same performance roughly as having lots writing, because actually, as far as the I/O system is concerned, there is one. It's the nodes that matter. They're the clients. Each computer is a separate node. However, actually coming back to what Angela said, each node on ARCHER2 has 2 network interfaces, whereas ARCHER only had 1. So actually, it might be better to have 2 MPI processors per node, not 1. But again, this is something we can test experimentally. But I think distributed I/O using MPI plus OpenMP should work fine. But it actually might be better to do 2 MPI processors per node than 1. I haven't had a chance to look at that yet. But I don't, in general, MPI plus OpenMP does not harm your parallel I/O, I don't believe. Okay, so Paul knows more about ADIOS. Paul saying ADIOS 2 allows aggregated configuration at runtime independently of the MPI settings. But the default is per node. The natural thing is to do 1 per node, but for 2 reasons, it might be better to do multiple aggregators per node. Perhaps the OSTs aren't the limiting factor, in which case you can have more write stream OST. Perhaps you increase the bandwidth of your node by using both network interfaces. I don't think you'll use by default if you only have 1 MPI process. But again, that's all to be investigated. So actually, the guest question of 1 MPI processor per node with many OpenMP threads. This isn't about I/O. The ARCHER2 nodes are quite complicated in terms of the way that the NUMA regions work. So actually, if you were to say what's the optimal setting of MPI plus OpenMP on ARCHER2 with no other evidence, I would say 8 MPI processes per node and 16 OpenMP threads per process should be okay, because fundamentally an ARCHER2 processor has lots of mini processors, each of which has about, or actually maybe it's more than that, maybe it should be 16 MPI plus 8 threads. It's not going to be hundreds of threads, you know, it's going to be of order, the sweet spot will be of order 8 or 16 threads per MPI process, is my hunch, because the architecture is quite complicated. This isn't an I/O statement, this is just on pure CPU speed. I mean, Archer was quite simple. It had 2 12-core processors, each of which was a NUMA node. ARCHER2 has 2 64-core processors, but each of those processors is actually a 64. It's actually 4 NUMA regions, each with 16 cores. Oh, I'm getting this wrong. And there's even another hierarchy to the L3 cache. I need to look at the diagram. But I think your codes will top out at 8 or 16 threads per process, probably. So I hope that was useful. Hopefully, I think the conclusions is useful. You know, for parallel to a shared single file, use a high-level parallel IO library, use collective tools, but stripe, because you know you may be able to improve if you're using a big package. To be well engineered, you may be able to improve your I/O performance by a factor of 12 by tapping one command. LFS set stripe -c -1 output directory may increase your I/O performance by more than an order of magnitude. That's definitely something to try. However, for serial I/O, if you're writing lots of files or using just normal I/O routines, i.e. not a parallel I/O library, but just fwrite or Fortran write, it's probably not worth striping the files. It's probably not going to help you. Okay, thanks everyone. Hope you found that useful, and keep an eye on the website for details of upcoming virtual tutorials, which will be focusing on the we'll have tutorials focusing on the transition from Archer to Archer 2, the 4 cabinet to production system, as soon as it comes into production service.